The original intent of the junction box required by National Electrical Code Section 555.13b4 was to provide a convenient and safe way to distribute power from a feeder cable to multiple branch circuits on a floating pier. However, with the advent of high-capacity power centers that are typically fed by their own dedicated feeders, the need for a separate junction box for power distribution has diminished. In addition, modern power centers often incorporate their own integral junction boxes, eliminating the need for a separate external junction box. These integral junction boxes are typically designed to accommodate multiple branch circuits and provide overcurrent protection for each circuit. As a result, it is reasonable to question whether the requirement for a separate junction box on floating piers remains necessary in all cases. In situations where power is distributed from a feeder cable to multiple power centers, each with its own integral junction box, the additional junction box required by National Electrical Code Section 555.13b4 may be redundant and unnecessary. However, it is important to note that the National Electrical Code does not explicitly address this issue, and the requirement for a separate junction box on floating piers remains in place. It is ultimately up to the authority having jurisdiction, or OJ, to determine whether the requirement is necessary in a particular installation. To delve deeper, let's consider the specific requirements outlined in the National Electrical Code and how they relate to floating piers and marinas. Section 555 covers the installation of electrical wiring and equipment in marinas, boatyards, floating buildings, and docking facilities. This section addresses the unique challenges posed by these environments, such as exposure to water, corrosive elements, and physical stress. The core purpose of Article 555 is to minimize hazards, specifically shock and fire hazards to people and property. It's important to remember that electricity and water are a dangerous combination, and corrosion can quickly compromise electrical connections. Within Section 555.13, the focus is on equipment grounding conductors. This is a critical safety measure that ensures a low impedance path for fault current to return to the source, which in turn facilitates the operation of overcurrent protective devices like circuit breakers and fuses. The goal here is to quickly de-energize a circuit in the event of a ground fault, minimizing the risk of electric shock. Now, let's zoom in on Section 555.13b4, which specifically addresses floating buildings. This section outlines requirements for the grounding and bonding of electrical systems on floating structures. Subsection B, which is the crux of the discussion, mandates the use of a junction box under certain conditions. The rule requiring the junction box is there to manage the transition from the feeder cable which supplies power to the floating pier to the branch circuits that serve individual loads, like shore power receptacles for boats or lighting fixtures. The junction box serves as a central point for terminating and distributing these circuits, ensuring proper connections and overcurrent protection. The original rationale behind requiring a junction box was multifaceted. Firstly, it provided a designated location for making electrical connections, reducing the likelihood of haphazard or unsafe wiring practices. Secondly, it allowed for the installation of overcurrent protection at the point where branch circuits originated, providing localized protection for each circuit. Thirdly, it facilitated the use of appropriately sized conductors for each branch circuit, optimizing efficiency and safety. However, as technology has advanced and the demands of modern marinas have evolved, the relevance of this requirement has come into question. Modern power centers, designed to deliver electricity to boats, often incorporate sophisticated features such as integral junction boxes, overcurrent protection, ground fault protection, and metering capabilities. These power centers effectively consolidate many of the functions that were traditionally handled by separate components, including the junction box specified in 555.13b4. In many cases, a marina might have individual power centers distributed along a floating pier, each serving a limited number of boatlets. These power centers are often fed by their own dedicated feeder cables, eliminating the need for a central junction box to distribute power to multiple branch circuits. The integral junction box within each power center provides the necessary connection points and overcurrent protection for the branch circuits that serve the adjacent boat slips. The question then becomes, is the separate junction box required by 555.13b4 truly necessary in this scenario? If each power center already provides a suitable junction box with overcurrent protection for its branch circuits, requiring an additional junction box may be redundant and add unnecessary cost and complexity to the installation. It is important to acknowledge the counter-arguments. Some argue that the separate junction box provides an extra layer of safety and redundancy. In the event of a failure within the power center's integral junction box, the separate junction box could potentially provide a backup connection point. Others emphasize the importance of maintaining consistency with the National Electrical Code requirements, arguing that any deviation from the code could compromise safety. Ultimately, the decision of whether to require a separate junction box in situations where power centers with integral junction boxes are used rests with the authority having jurisdiction, or ORG. The AHJ is the local electrical inspector or other official responsible for enforcing the National Electrical Code. The AHJ has the authority to interpret the code and make judgments based on the specific circumstances of each installation. When evaluating a proposal to omit the separate junction box required by 555.13b4, the AHJ will likely consider several factors. These include the design and construction of the power centers, the qualifications of the electrical contractor, and the overall safety of the installation. The AHJ may also request additional information or documentation to support the proposal. If the AHJ is satisfied that the power centers provide an equivalent level of safety and functionality as a separate junction box, they may approve the omission of the requirement in 555.13b4. However, the AHJ may also impose additional conditions or requirements to ensure the safety of the installation. One approach that can be taken is to submit a formal request for interpretation to the National Fire Protection Association, or NFPA, which is the organization that publishes the National Electrical Code. The NFPA can provide guidance on the intent of the code and how it applies to specific situations. While an NFPA interpretation is not legally binding, it can carry significant weight with the AHJ. Another approach is to work closely with the electrical contractor and the power center manufacturer to develop a comprehensive design that meets the intent of the National Electrical Code. This may involve providing detailed documentation, conducting testing, or implementing additional safety measures. In conclusion, the need for a separate junction box on floating piers, as required by National Electrical Code Section 555.13b4, is a complex issue that depends on the specific circumstances of each installation. While the original intent of the requirement was to provide a safe and convenient way to distribute power to multiple branch circuits, the advent of modern power centers with integral junction boxes has raised questions about its continued relevance in all cases. Ultimately, the decision rests with the authority having jurisdiction, who will consider the design and construction of the electrical system, the qualifications of the electrical contractor, and the overall safety of the installation. It is always recommended to consult with a qualified electrical engineer and the local AHJ to ensure compliance with all applicable codes and regulations. Now let's elaborate on the technical details surrounding the requirements for junction boxes and their proper installation in marine environments, drawing further insight from the National Electrical Code and industry best practices. Firstly, the National Electrical Code mandates that all electrical equipment installed in marinas and boatyards be suitable for the wet and corrosive environment. This typically means using enclosures made of corrosion-resistant materials such as stainless steel, fiberglass, or non-metallic materials specifically listed for marine use. The junction box itself must be appropriately rated for the environment. This is usually indicated by an ingress protection, or IP, rating, which specifies the degree of protection against the ingress of solid objects and liquids. For example, an I-66 rated enclosure is dust-tight and protected against powerful water jets, making it suitable for many marina applications. In addition to material selection, the construction of the junction box is also important. The enclosure must be designed to prevent the entry of water, even when subjected to wave action or heavy rain. This often involves the use of gaskets, seals, and watertight connectors. The cover of the junction box should be securely fastened with screws or bolts to prevent accidental opening. When selecting a junction box, it is crucial to consider the number and size of conductors that will be terminated within it. The box must be large enough to provide adequate space for the conductors, connectors, and any other components that will be installed inside. National Electrical Code Section 314.16 provides detailed requirements for calculating the minimum box size based on the number and size of conductors. It is also important to ensure that the junction box is properly grounded. The grounding conductor must be securely connected to the box using a listed grounding connector. This connection provides a low impedance path for fault current to return to the source, which is essential for the operation of overcurrent protective devices. Now, let's delve into the specific requirements for wiring methods in marinas and boatyards. National Electrical Code Section 555.11 specifies the types of wiring methods that are permitted in these locations. In general, wiring must be installed in rigid metal conduit, intermediate metal conduit, rigid non-metallic conduit, or cable listed for wet locations. Flexible cords and cables are permitted for certain applications, such as connecting portable equipment, but they must be of the extra hard usage type and listed for marine use. All wiring must be supported and secured in accordance with the National Electrical Code requirements. This typically involves the use of clamps, straps, or other hardware to prevent the wiring from sagging or rubbing against other objects. The wiring must also be protected from physical damage. This may involve the use of conduit guards or other protective measures. When running wiring underground, it must be buried at a sufficient depth to protect it from damage. National Electrical Code Section 300.5 provides detailed requirements for underground wiring. In addition to the general wiring requirements, there are also specific requirements for wiring on floating structures. National Electrical Code Section 555.13 requires that wiring on floating structures be installed in a flexible wiring method. This is to accommodate the movement of the structure due to waves and tides. The flexible wiring method must be listed for wet locations and be resistant to corrosion. The wiring must also be supported and secured to the structure in a manner that prevents it from chafing or rubbing against other objects. Furthermore, it is important to consider the voltage drop in the wiring. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. National Electrical Code Section 210.19 AM provides guidelines for limiting voltage drop in branch circuits. In general, the voltage drop should not exceed 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is important to use conductors of adequate size and to keep wiring runs as short as possible. Finally, it is essential to ensure that all electrical work in marinas and boatyards is performed by qualified and licensed electricians. These professionals have the training and experience necessary to install electrical systems safely and in accordance with all applicable codes and regulations. They can also provide valuable advice in the selection of equipment and wiring methods. Let's move on to an extended discussion on the selection and implementation of overcurrent protection within marine electrical systems, further grounded in the National Electrical Code guidelines and the pursuit of optimal safety. Overcurrent protection is a cornerstone of electrical safety, designed to protect wiring and equipment from damage caused by excessive current flow. This protection is primarily achieved through the use of circuit breakers and fuses, which are designed to interrupt the flow of current when it exceeds a predetermined level. In marine environments, the selection and placement of overcurrent protection are particularly critical due to the high risk of electrical shock and fire hazards associated with water and corrosive conditions. The National Electrical Code provides detailed requirements for overcurrent protection in Article 240, which covers the types of overcurrent protective devices, their ratings, and their application. The basic principle of overcurrent protection is that the overcurrent protective device must be sized to protect the conductor it is serving. This means that the ampacity of the conductor must be equal to or greater than the rating of the overcurrent protective device. The ampacity of a conductor is its current carrying capacity, which is determined by its size, insulation type, and ambient temperature. National Electrical Code Section 310.15 provides tables that list the ampacities of various types of conductors. When selecting an overcurrent protective device, it is also important to consider its interrupting rating. The interrupting rating is the maximum amount of fault current that the device can safely interrupt without being damaged. The interrupting rating must be equal to or greater than the available fault current at the point of installation. The available fault current is the amount of current that would flow in a circuit under fault conditions, such as a short circuit. This can be calculated using engineering methods or determined through fault current studies. In marine electrical systems, it is common to use a combination of circuit breakers and fuses to provide overcurrent protection. Circuit breakers are resettable devices that can be tripped manually or automatically in response to an overcurrent. Fuses are one-time devices that must be replaced after they have blown. Circuit breakers are generally preferred for branch circuits because they can be easily reset, while fuses are often used for feeder circuits because they provide a higher interrupting rating. The placement of overcurrent protective devices is also critical. Overcurrent protective devices must be installed at the point where conductors receive their supply and at the point where conductors are reduced in size. This ensures that each section of the wiring system is protected against overcurrent. In marine electrical systems, it is common to install overcurrent protective devices in panel boards, which are enclosures that house multiple circuit breakers or fuses. Panel boards are typically located at the main service entrance and at various distribution points throughout the marina. In addition to conventional overcurrent protection, ground fault circuit interrupters, or GFCIs, are also required in marine electrical systems. GFCIs are devices that detect small amounts of current leakage to ground and interrupt the circuit, preventing electric shock. National Electrical Code Section 555.19 requires GFCIs to be installed on all receptacles that supply power to boats. GFCIs are highly sensitive devices that can detect current leakages as low as 5 mA. They are designed to trip quickly, typically within 25 milliseconds, to prevent serious injury. It is important to test GFCIs regularly to ensure that they are functioning properly. This can be done using a GFCI tester, which simulates a ground fault condition and verifies that the device trips. In summary, overcurrent protection is a critical safety feature in marine electrical systems. The selection and placement of overcurrent protective devices must be carefully considered to protect wiring and equipment from damage and to prevent electrical shock. The National Electrical Code provides detailed requirements for overcurrent protection, and it is essential to comply with these requirements. Moving further into the discussion of grounding and bonding within marine electrical systems, it is crucial to recognize that these practices form the backbone of electrical safety in such environments. Grounding and bonding are designed to create a low impedance path for fault current to return to the source, which in turn facilitates the operation of overcurrent protective devices and minimizes the risk of electric shock. The National Electrical Code provides comprehensive requirements for grounding and bonding in Article 250. Grounding refers to the connection of electrical equipment and wiring to the earth. This connection is typically made through a grounding electrode, such as a ground rod or a metal water pipe. The purpose of grounding is to provide a reference point for the electrical system and to limit the voltage on equipment enclosures. Bonding refers to the connection of various metal parts of the electrical system together. This includes equipment enclosures, conduit, and other metal components. The purpose of bonding is to create an electrically continuous path that allows fault current to flow back to the source. In marine electrical systems, grounding and bonding are particularly important due to the presence of water and the potential for corrosion. The National Electrical Code requires that all metal parts of the electrical system be bonded together, including the metal frames of boats. This is to prevent stray currents from flowing through the water, which can create a shock hazard. The bonding conductor must be sized in accordance with National Electrical Code Table 250.122 and must be made of copper or other corrosion-resistant material. In addition to bonding the metal parts of the electrical system, it is also important to ground the metal parts of the marina structure. This includes the metal frames of docks, piers, and other structures. The grounding conductor must be connected to a grounding electrode, such as a ground rod or a metal water pipe. The grounding electrode must be located as close as possible to the electrical service entrance. It is also important to consider the potential for galvanic corrosion in marina electrical systems. Galvanic corrosion occurs when two dissimilar metals are in contact with each other in the presence of an electrolyte, such as seawater. The more active metal will corrode, while the less active metal will be protected. To prevent galvanic corrosion, it is important to use compatible metals for electrical connections and to isolate dissimilar metals from each other. This can be done by using insulating washers, sleeves, or other insulating materials. In summary, grounding and bonding are essential for electrical safety in marina electrical systems. These practices create a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protective devices and minimizes the risk of electric shock. The National Electrical Code provides detailed requirements for grounding and bonding, and it is essential to comply with these requirements. Let's address the topic of electrical safety inspections and maintenance procedures specifically tailored for marine environments. Regular inspections and maintenance are crucial for ensuring the continued safe and reliable operation of electrical systems in marinas. The corrosive environment and the proximity to water create unique challenges that require a proactive approach to electrical safety. Electrical safety inspections should be conducted by qualified and licensed electricians who are familiar with the National Electrical Code requirements for marinas. The inspections should cover all aspects of the electrical system, including the service entrance, distribution panels, wiring, receptacles, lighting, and grounding system. During the inspection, the electrician should look for any signs of damage, corrosion, or deterioration. This includes cracked or broken insulation, loose connections, corroded terminals, and damaged equipment enclosures. The electrician should also test the operation of overcurrent protective devices, such as circuit breakers and fuses, to ensure that they are functioning properly. Ground fault circuit interrupters, or GFCIs, should also be tested to verify that they are tripping at the correct current level. In addition to visual inspections and testing, the electrician should also perform insulation resistance tests in the wiring. Insulation resistance tests measure the resistance of the insulation surrounding the conductors. Low insulation resistance indicates that the insulation is deteriorating and that there is a risk of electrical shock. The electrician should also inspect the grounding system to ensure that it is properly connected and that the grounding electrodes are in good condition. The grounding electrodes should be tested to verify that they are providing a low impedance path to ground. Any deficiencies found during the inspection should be corrected promptly. This may involve repairing or replacing damaged equipment, tightening loose connections, cleaning corroded terminals, or upgrading the grounding system. In addition to regular inspections, it is also important to perform routine maintenance on the electrical system. This includes cleaning equipment enclosures, lubricating moving parts, and tightening connections. The electrical system should also be protected from the elements. This may involve installing weatherproof covers on receptacles, protecting wiring from physical damage, and providing adequate drainage to prevent water from accumulating around electrical equipment. Marine operators should also educate boat owners about electrical safety. This includes providing information on the proper use of shore power receptacles, the dangers of electrical shock, and the importance of maintaining their boat's electrical system. Boat owners should be encouraged to have their boat's electrical system inspected regularly by a qualified electrician. In summary, electrical safety inspections and maintenance procedures are essential for ensuring the continued safe and reliable operation of electrical systems in marinas. Regular inspections, routine maintenance, and education of boat owners are all important components of a comprehensive electrical safety program. Let us explore the impact of technological advancements on marine electrical systems. The evolution of technology has brought about significant changes in the design, operation, and safety of marine electrical systems. These advancements offer numerous benefits, including improved efficiency, enhanced safety, and increased reliability. One of the most significant technological advancements in marine electrical systems is the development of smart power pedestals. Smart power pedestals are equipped with advanced metering, monitoring, and control capabilities. They can measure the amount of electricity consumed by each boat, monitor voltage and current levels, and remotely control power to individual slips. Smart power pedestals can also provide valuable data on energy consumption patterns, which can be used to optimize energy management and reduce costs. Another important technological advancement is the use of solid-state lighting. Solid-state lighting, such as light-emitting diodes or LEDs, is far more energy efficient than traditional lighting technologies. LED also have a much longer lifespan, which reduces maintenance costs. In addition to smart power pedestals and solid-state lighting, there have also been advancements in wiring methods and materials. New types of cables and connectors offer improved resistance to corrosion and physical damage. These materials can significantly extend the lifespan of the electrical system and reduce the risk of failures. Technology has also played a role in improving the safety of marine electrical systems. Ground fault circuit interrupters, or GFCIs, are now more sensitive and reliable than ever before. Arc fault circuit interrupters, or SIs, are also being used to protect against fires caused by arcing faults. These devices can detect dangerous arcing conditions and quickly interrupt the circuit, preventing a fire from starting. Furthermore, wireless technology is being used to monitor and control marine electrical systems remotely. This allows marine operators to quickly respond to problems and to optimize energy usage. Wireless sensors can be used to monitor voltage, current, temperature, and other parameters. This data can be transmitted to a central monitoring station, where it can be analyzed to identify potential problems. In summary, technological advancements are transforming marine electrical systems. These advancements offer numerous benefits, including improved efficiency, enhanced safety, and increased reliability. As technology continues to evolve, marine electrical systems will become even more sophisticated and efficient. Lastly, consider the important role of collaboration between electrical engineers, contractors, and marine operators in ensuring electrical safety. Ensuring electrical safety in marinas requires a collaborative effort between electrical engineers, contractors, and marina operators. Each party has a unique role to play in creating and maintaining a safe and reliable electrical system. Electrical engineers are responsible for designing the electrical system and ensuring that it meets all applicable codes and standards. They must consider the specific environmental conditions of the marina and select equipment and materials that are suitable for the wet and corrosive environment. Electrical engineers must also perform calculations to ensure that the electrical system is properly sized and that it can handle the expected load. Electrical contractors are responsible for installing the electrical system in accordance with the design and specifications. They must be licensed and qualified to perform electrical work in marinas. Electrical contractors must also be familiar with the National Electrical Code requirements for marinas. During the installation process, electrical contractors must carefully inspect all equipment and materials to ensure that they are in good condition. They must also follow proper wiring practices and ensure that all connections are tight and secure. Marina operators are responsible for maintaining the electrical system and ensuring that it is operated safely. They must perform regular inspections to identify any potential problems. Marina operators must also educate boat owners about electrical safety and ensure that they are using shore power properly. In addition to their individual responsibilities, electrical engineers, contractors, and marina operators must also work together to ensure electrical safety. This includes communicating effectively, sharing information, and coordinating their activities. For example, electrical engineers should consult with marina operators to understand their specific needs and concerns. Electrical contractors should keep marina operators informed of the progress of the installation and any potential problems. Marina operators should provide feedback to electrical engineers and contractors about the performance of the electrical system. Collaboration is also important during the design phase. Electrical engineers should work with marina operators to develop a design that meets their needs and that is easy to maintain. Electrical contractors should review the design to identify any potential problems and to suggest improvements. Collaboration is essential during the maintenance phase as well. Marina operators should report any electrical problems to electrical contractors promptly. Electrical contractors should respond to these reports quickly and efficiently. In summary, collaboration between electrical engineers, contractors, and marina operators is essential for ensuring electrical safety in marinas. By working together, these parties can create and maintain a safe and reliable electrical system.